Hello everyone, welcome to the final lecture of this first module on fundamental of measurement systems, and we are discussing the course on measurement and instrumentation. So, today's plan is we will discuss about different errors and we will also talk about the dynamic characteristic which we have not discussed yet. We are only discussing the static characteristics. We will also see the measurement systems it can be electrical in nature, it can be say mechanical in nature, because we will be utilizing these measurement systems in our next module, which is on analog meters. Okay. So, let us start our discussion on errors. Okay. In errors, let us first talk about different type of errors. So, error may arise in an instrument from different sources and are usually classified as gross error, a systematic error and a random error. Okay. So, let us see them one by one. First, let us talk about gross error. Okay. So, this class of error mainly covers human mistakes, particularly in reading the instrument and recording. There can be some calculation mistakes or calculating results from the measurement that you have done. This is also classified under gross error. Okay. So, basically the experimenter may grossly misread the scale of the measurement tool, okay, and that is why the name is like gross error. Okay. Let us see this with an example. A typical example can be like say due to oversight, the observer may read the temperature from a thermometer in place of 31.5 degrees Celsius say to 21.5 degrees Celsius. So, he has read the temperature as 31.5 degrees Celsius, while the actual reading on the thermometer was only 21.5 degrees Celsius. Okay. This is kind of a common mistake that an observer can do. Okay. So, if you see this kind of mistake, I mean this is just an example 31.5, 21.5 he may write 12.5 or say 51.5, okay, it can be anything. Okay. So, but one thing is clear from this, that gross error may be of any amount. Right. So, there is no fixed deviation like he will record only 31.5, he can record, as I have mentioned, 12.5 as well as he can write 51.2 or some anything. Okay. So, one thing should be very clear, that the gross error may be of any amount and therefore, their mathematical analysis is impossible. It is really impossible to predict that what observer is going to record. Okay. So, then how to avoid this gross error from the measurement? Two approaches can be there. One is great care should be taken in reading and recording the data. So, when the observer is taking the data, he should put more attention on recording the data, as well as the other approach can be like you can have multiple readings. So, 2, 3 or even more readings should be taken for quantity which is under measurement. So, by this you avoid any confusion. Say for example, for this 21.5, if you have taken the reading multiple time, okay, at all if you find 31.5 in the reading, you may simply remove that thinking that it must be a kind of gross error. Fine. So, this is the two approaches by which gross error can be avoided. Okay. The second is the systematic error. Okay. So, systematic error refers to a consistent repeatable deviation from the measured value and the true value. Okay. This is caused by say a flaw in the measurement system. The flaw can also be in the method or in the environmental conditions. Okay. Systematic errors are divided into three different categories. Okay. It can be instrumental error, you can have environmental error and observational error. All these three are categorized as systematic error. Okay. Let us see all this systematic error one by one. The first one is the instrumental error. Okay. This instrumental errors arise due to three different reasons. First is due to the inherent shortcoming in the instrument. Okay. This can also propagate due to misuse of the instrument, and of course, loading effect of the instrument is another cause of the systematic error. Okay. So, let us see these three reasons in little brief. Okay. Say when I say inherent shortcoming in the instrument, means that the shortcoming can be either due to construction of the instrument overall, or it can be due to calibration, or it can also be due to the operation of the instrument. Okay. So, the shortcoming in the instrument does not necessarily mean the construction, it also mean that calibration as well as operation of the instrument. Okay. These errors may cause the instrument to read either too high or too low. Okay. So, for example, we have say a spring in a system. Okay. In a electrical system, you know that all this electrical system had needle kind of structure. We have discussed this in detail. Okay. So, this is of course connected through a spring. Okay. Now, this is mostly used for producing controlling torque. Okay. Now, if this spring is of say there is some error in this spring itself, it has become stiff, or say this is having different spring constant as compared to what was desired. So, there is a construction demerit in the instrument. Okay. Because of this, the instrument will behave totally differently. Okay. So, if the spring has gone weak in a say PMMC instrument, the instrument will automatically read always a high value. Okay. So, the idea is to minimize this kind of error, the instrument has to be recalibrated, and during the recalibration you will easily find that what has gone in the instrument. Okay. And if you do this kind of thing, okay, you can at least minimize the error. Okay. Second is the misuse of instrument. Okay. So, error caused in a measurements are due to the fault of the operator than that of the instrument. Okay. So, you can think like a good instrument used in an unintelligent way can give you erroneous results. Okay. So, misuse of instrument has to be avoided when you work in a laboratory. Okay. So, examples that may be cited for this misuse of instrument can be like a failure to adjust the zero of the instrument. So, if you have not set it to zero value, okay, and you are carrying the previous value, of course, you will your results will be erroneous in nature. Okay. Say if you do not do the initial adjustment of the instrument, okay, the result will be erroneous, and again this is categorized under the misuse of the instrument. Okay. Then we have loading effect. Okay. So, loading effect, we are taking this since last 2-3 lectures. Okay. Say a well calibrated voltmeter can give a misleading voltage reading when connected across a high resistance circuit, while the same voltmeter when connected to a low resistance circuit may give a more dependable reading. Okay. Let us try to understand this with an example. Okay. Now, consider that you have say there is a high resistance circuit, say there is some circuit and this is the resistance, say this resistance is say 1 mega ohm. Okay. Now, I have connected a voltmeter across it to read the voltage across this resistor, say I am calling this R1. Okay. And the resistance of this voltmeter, say it is R2. Now, R1 I am considering it as a high resistance, so it is say 1 mega ohm. Okay. The resistance of this voltmeter I am taking it as say 100 kilo ohm. Okay. Now, this is this voltmeter is of course connected in parallel to this resistance R1. Okay. Now, if I calculate the equivalent resistance, okay, this equivalent resistance, what it will be? Say it will be 1 mega ohm into, say this is 100 kilo ohm, so it is also 0.1 mega ohm. Okay. So, 1 mega ohm into 0.1 mega ohm divided by 1 mega ohm plus 0.1 mega ohm. This is 0.1 by 1.1. It is around 0.09 mega ohm. Okay. So now your R equivalent is 0.09 mega ohm, which is far from the actual reading. Okay. Now consider that this resistance is not very high. Okay. Now the voltmeter is connected to a low resistance. Now this low resistance, say this is R2 and say this is a low resistance value, say 100 ohm. Okay. Now this voltmeter is connected in parallel to it, and say this is again same voltmeter, say 100 kilo ohm. Okay. Now if I calculate the equivalent resistance, so R equivalent is say R2 into so this is, I am calling this R3, this was R2. So this is R2 into R3 by R2 plus R3, right. So it will be like 100 ohm plus 100 kilo ohm divided by 100 kilo ohm plus this is 100 ohm into 100 kilo ohm divided by 100 kilo ohm plus 100 ohm, right. So if you calculate this, this value is around, say this I am calling it say 0.1 kilo ohm, right, into 100 kilo ohm and divided by 100.1, right. So 10 kilo ohm divided by 100.1 kilo ohm. So this value is near to the actual value, right. So if you see, the more accurate result that you are getting is in the case when you have low resistance in compared to the high resistance value. So it's always there that when you connect this is all about because your voltmeter is loading the circuit. Okay. So always precaution has to be taken while connecting these instruments like this. Okay. So it's very clear that when voltmeter is connected across a circuit where it's a high resistance circuit, means that it will give you your erroneous result, while if it is low resistance circuit, lower than the voltmeter resistance, it will give you much better or much accurate result. Okay. So this example illustrates that the voltmeter has a loading effect on the circuit. Okay. This is altering the actual circuit condition by the measurement process. Okay. So this is the three different instrumental error that we have just seen. Okay. This is due to inherent shortcoming in the instrument, due to the misuse of the instrument, okay, and due to the loading effect of the instrument, right. Now let us see the other kind of systematic error. We have just covered the instrumental errors. The other kind of errors are environmental errors and observational errors. Okay. So let us see what I mean by the environmental errors. Okay. So these errors are due to conditions external to the measuring device, including condition in the area surrounding the instrument. Okay. So these can be the effects of external ambient and external physical conditions like condition of the temperature, pressure, humidity, the dust in the ambient, the vibration in the ambient, okay, or of say any external electromagnetic field or even electrostatic field or any only magnetic field is there or not. Okay. So they may have adverse effect on the measurement. Okay. So the corrective measure employed to eliminate or at least to reduce these undesirable effect, particularly the environmental one, is to have arrangements that keep the condition as nearly constant as possible for the equipment when it operates. Okay. Or you can also think of equipments which are immune to these effects, which is rarely found. Okay. So in case it is suspected that external magnetic or say electrostatic fields can affect the reading of the instrument, magnetic shielding or electrostatic shielding can be provided. Okay. There are methods to have computed corrections of the result. If I am able to assess the ambient condition, maybe the condition of the temperature or condition of the pressure or the humidity condition in the vicinity of the equipment or the instrument, I may have a computational correction employed to the instrument. Okay. The third type of systematic error is the observational error. Okay. So, let us quickly see what do we mean by the observational error. Okay. So, there are many sources of observational error. Just one example we are giving. Okay. Say the pointer of a voltmeter say rests slightly above the surface of the scale mostly. Okay. So, when you see this pointer from different reason, okay, you may be reading or recording the data erroneously. Okay. So, if you are seeing this from this side or this side, okay, because this voltmeter scale is covered by some mirror for its protection, right. So, it will have a parallax. Okay. So, an error on account of parallax will be incurred automatically unless the line of vision of the observer is just exactly above the pointer. So, this way of measuring this analog pointer's position, or if you are seeing from this position, these all are going to give you wrong result. So, correct reading will be if you are just watching from top of it. Okay. So, this will give you correct reading, otherwise it will give you both the readings will give you incorrect result. Okay. So, this parallax error is kind of observational error, right. Then there is another kind of error, which is the random error. Since these errors remain even after the systematic errors have been taken care of, we call these errors as residual errors or random errors. So, any error apart from these things that we have discussed is mostly considered as the random one. Okay. So, the quantity which is being measured is affected by we know that many happenings throughout the universe. Okay. So, we are aware of and account for some of the factor which is influencing the measurement, but of course, we rest of them we are unaware of. Okay. And because of that, these random errors occurs. Okay. So, the happening or disturbances about which we are unaware are lumped together as a random or residual error. Okay. So, hence the error caused by this happening is not not known in nature. Okay. But of course, it exists. So, you will find lot of equipment with random errors. Okay. We will see for particular equipment that how to or for particular instrument that how to tackle these random errors. Okay. So, I hope that the concept of errors is clear to you. Okay. We have similarly finished the concept of noise. Okay. So, with this I think we have covered the static characteristics in little detail. Okay. Apart from this, some instrument may have a specific static characteristic. Okay. So, those characteristics we will discuss when we will talk about that particular instrument. Okay. So, let us see a dynamic characteristic also. Okay. So, any measurement system when are subjected to inputs which are not static, mostly in dynamic in nature. Okay. So, the input varies from instant to instant, and therefore, the output of course should vary. Okay. So, the behavior of the system under such condition is described by the dynamic response. Okay. So, the response is basically the summation of the two factors, which is transient response and the steady state response. So, if I take an example, if CT C is a function of t is the total time response of a system, CT can be written as a summation of CT plus CSS. Of course, both are function of time. Okay. So, in this case the CT denotes the transient portion of response, while the CSS shows the steady state portion of the response. So, the total time response is collective behavior of its transient and its steady state response. Okay. So, the transient response is defined as the part of response which goes to 0 as time becomes large. Okay. So, mostly the total response, the CT, okay, when the time goes to infinity, this particular value will only be this CT value will become 0. Okay. So, you have only CSS component in the CT. Okay. Similarly, after a long time the system response in the steady state. Okay. So, when you have this t approaching infinity, that time you have only the steady state response. But when time is limiting to 0, means that time you are more concerned about the transient response of the device or the instrument. Okay. So, in measurement system, the steady state response is simply the response when time reaches infinity, while when it was 0, it is mostly transient in nature. Okay. So, right now we are discussing about the dynamic characteristic of the measurement system. Okay. So, there are 4 different dynamic characteristics of an instrument. One is the speed of response, the second one is the measuring lag, okay. Then we have fidelity and the dynamic error. Okay. So, let us talk about them in a little brief. Okay, so that we also understand dynamic characteristic of the instrument along with its static characteristics. Okay. So, let us first talk about the speed of response. Okay. So, speed of response is defined as the rapidity with which a measurement system respond to change in the measured quantity. Okay. Say this is one example of a measurement system. Say the measurement system is to measure say the concentration of gas say in this cylinder. Okay. Now, this is done using a sensor, and then you have complete system with the transducer and a signal conditioning circuit and all. Okay. Now, when say the gas is in, so this point say this gas is this sensor is exposed to gas. Okay. So, this is the sensor and this say this is exposed to gas. Okay. What will happen, for example, the resistance of the sensor decreases. Okay, due to some chemi-resistive behavior of this device. Okay. Now, this value will decrease to certain value where it will kind of saturate. Okay. And then when you switch it off, it should reach to its baseline position. Okay. And this was the baseline position. Okay. Now, usually when you have given the gas to the point where it has reached the saturation is the response time. Usually it is taken as 10% to 90% and similarly 90% to 10%, okay, to avoid any kind of unsaturation. Okay. So, in this case, this is the response time and recovery time of the measurement system. Okay. Sometime it is also called rise time and fall time. Okay. The second is the measuring lag. Okay. This is again the second dynamic characteristic. Okay. So, it is the retardation or delay in the response of a measurement system to change in the measuring quantity, okay, or the measured quantity. Okay. So, the measuring lags can be of 2 type. It can be a retardation type lag or it can be a time delay type lag. Okay. So, let us see what is retardation type lag. Okay. So, in this case, the response of the measurement system begins immediately after a change in the measured quantity has occurred. Okay. But the response is slow and it reaches to the final value. Okay. So, please note this, the response of the measurement system begin immediately after a change. So, looks like there is no retardation, but the retardation comes after. Okay. So, because the response is slow. Now, say take an example like if this is say water, okay, and I want to measure the temperature of this water with some say thermometer. Okay. Now, when I put this thermometer inside the water, what will happen is the mercury level will rise immediately to certain value, and after that it so it is responding immediately, right, and then it slowly increases to its final value and then it saturates, okay, giving you the final reading of the temperature of the water. Okay. So, this kind of lag is known as retardation type lag. Okay. Then second is time delay lag. Okay. So, in this case, the response of the measurement system begins after the dead time, after the application of the input. Dead time simply shifts the response of the system along the time scale. Okay. So, an example of transmission line can be taken, say if there is a long transmission line, okay, you pass a certain signal and for some time there will be no output and suddenly there is output. Okay. So, this kind of measuring lag is known as the time delay lag. Okay. Then there is a concept of fidelity, which is also a dynamic characteristic. Okay. So, it is defined as the degree of closeness to which a measurement system indicates change in the measured quantity without any dynamic error. Okay. What is dynamic error? We will see. Okay. Suppose if a linearly varying quantity is applied to a system and if the output is also a linearly varying quantity, the system is said to have 100% fidelity. Okay. So, ideally a system should have 100% fidelity and the output should appear in the same form as that of input and there is no distortion produced in the signal by the system. Okay. So, in the definition of fidelity, any time lag or phase difference between output and input is not included. Okay. So, you are not taking care of any time lag or phase difference. What you are only worried is about if it is following input or not. Okay. So, there can be two kind of fidelity: high fidelity when you have around 100% fidelity, and then you have low fidelity when your fidelity is not 100%, right. Then finally, we have dynamic error, which is again a dynamic characteristic. So, it is the difference between the true value of the quantity under measurement, which is changing with time, and the value indicated by the measurement system if you are not considering any static error. Okay. Now, this dynamic error is also known as the measurement error, and the total dynamic error of the instrument is the combination of its fidelity and the time lag or phase difference between the input and output of the system. Okay. So, I hope that the dynamic characteristics, the four different dynamic characteristics are clear to you. Okay. We have also covered the static characteristics in the previous lectures. Okay. So, the dynamic behavior of the measurement system is studied in two different domains. You can study it in the time domain as well as you can study in the frequency domain. Okay. So, we will be discussing the behavior of the measurement system in different domain depending on our convenience. Okay. And we will take this whenever we describe a particular instrument. Okay. Let us quickly see different part of a measurement system, because since we have covered the characteristics of the measurement system, now it is time to move to actual meters or actual measurement system. Okay. Because the concept of different characteristic including static and dynamic is clear to me. Okay. The concept of noise and errors are also clear to me. So, I am now ready for a holistic study of a measurement system. Okay. So, measurement system that we will deal may have electrical components or electrical or it can be entirely an electrical system, or it can have a mechanical part, mechanical system. Okay. We may also have to deal with thermal systems. Okay. When I say electrical networks or say electrical systems, this kind of circuitry, like this is a series electrical circuit. You may also have say L and C, this kind of, we may also come up with this kind of electrical system, and for all this system we can write the equations like this. Okay. Using simple KCL or KVL, this is written in the time domain, for example. So, this ET is written as this L di by dt plus R I t plus 1 by C integral of it into dt, or you can also write it in terms of charges. So, E can be given as L d square q by dt square plus R d q by t plus q by C. where charge is the integral of this current over the time, and I is or dq by dt. Okay. So, this is one way of representing any electrical system. Okay. Similarly, you can have this kind of system which is in parallel, or you can have a combination of series or parallel configuration of this electrical component for the electrical systems. Okay. We may also come up with the mechanical system. So, the mechanical system can be two type: mechanical translational system and mechanical rotational systems. Okay. So, translation basically is defined as a motion that takes place along a straight line, right. So, the three basic elements involved in a translation motion is a mass and a spring for providing the restoration, and then we have a friction for opposing forces. Okay. So, you have this movement, you have, when you apply a force, you have some displacement, and spring will try to bring it to its original position, and then you have a certain kind of friction. So, we will be using this kind of system when we will talk about some instrument which uses mechanical translational system. Okay. We may also come up across mechanical rotational system. So, rotational system are very similar to the translational system, except for the basic difference that torque equations are written in place of the force equations. Okay. So, you have to deal it with the torque and subsequent quantities like displacement, velocity and acceleration are termed in terms of angular quantity and so. Okay. Then third kind of systems that we may deal is the thermal systems. Thermal systems are those which involve the transfer of heat from one substance to another, and the thermal systems may be analyzed in terms of electrical parameters like in terms of resistance and capacitances, and this is not that difficult. What we have to consider that the resistance of heat flow in a material. So, if you take those considerations, it can be of course written in terms of resistances and capacitances. So, we will talk about these parts of measurement system when we will discuss certain meters which will employ this kind of elements, okay, or this kind of systems. Okay. So, we will be using, I think, all this or 3 or 4 systems that we have just seen from our next lecture. Okay. So, we will again meet in the second module where we will actually discuss about analog meters. Thank you.